In a molecule of ethanol, there are 3 unique hydrogen or proton environments. The first, the hydrogen in the OH group, the second, the 2 hydrogens bonded to the carbon that is bonded to the OH group, and the third, the 3 hydrogens bonded to the carbon that is bonded to the first carbon. This would give 3 peaks in a standard proton NMR spectra, 1 for each hydrogen environment. However, the peak splitting for each of these will be different, and we can use the n+1 rule to predict the peak splitting that we would expect to see. The first hydrogen isn't bonded to a carbon, meaning there are no adjacent carbons bonded to it either. As a result, n must be 0. Remember, n+1 is the number of times the peak gets split, meaning 0 + 1 is 1 peak, a singlet. No peak splitting has occurred. The second hydrogen environment, the CH2 group, does have an adjacent non-equivalent carbon atom that it is bonded to, and this carbon has 3 hydrogens bonded to it, meaning here n equals 3. Again, n+1 is the number of times the peak gets split. 3 + 1 is 4, a quartet. The final hydrogen environment, the CH3 group, has an adjacent non-equivalent carbon atom that it is bonded to, the CH2 group carbon. This carbon has 2 hydrogens bonded to it, meaning n equals 2. 2 + 1 is 3, meaning the peak gets split into 3, a triplet. Really important to notice here, however, that the number of times a peak gets split isn't based on the number of hydrogen atoms in that environment. It's based solely on the number of hydrogens bonded to adjacent non-equivalent carbon atoms. You gain no information about the number of hydrogen atoms in the environment the peaks are referring to, without using the ratio of areas under each peak in the spectra. For example, for ethanol, the ratio of areas under each peak will be 1 to 2 to 3, telling us that there is 1 hydrogen in the first environment, 2 in the second, and 3 in the third.